The first type of solutions that we can build are solutions to first order linear ODEs. So these are a lot of words. Let's try to break them down. ODEs. So we're looking for something, a function y of only one variable. We'll call this variable t. First order. It means that we're taking all possible derivatives up to the first order. So we're taking t, y, and y prime. Linear. Well, linear means that it has to have the form y prime equals something times y plus something else. These two somethings do not depend on y nor y prime, but can depend on the time. So if we put everything together, what we're looking for, and I'm flipping things around to make it easier when we're looking for the solution, what we're looking for is a solution to y prime plus a function of t times y equals a function of t. Let's look at an example. We're having this ODE. We have a y prime multiplied by 4 plus t squared. We add 2ty, and we want this to be equal to 4t. And if we look at the first side of the equation, we might notice that this can be rewritten as the derivative with respect to time of 4 plus t squared multiplied by y. And the right-hand side stays the same. But if on one hand we have the derivative with respect to time, then we can integrate with respect to time, both sides. And on the left side, well, derivative and integral cancel away. So we can just integrate the right-hand side that we know, and we have a formula. We have 4 plus tau squared multiplied by y equals the solution of the integral. Notice that here we have a plus c popping up. The plus c actually comes from the left-hand side because we don't know the value of y at 0. This is an important element, that plus c, but the right-hand side becomes 4 multiplied by tau squared divided by 2 plus c. And if we turn things around and we change tau into a t again, then we have a formula for the solution of our ODE. Yt equals 2t squared over 4 plus t squared plus c over 4 plus t squared. Now, I said that when we have a solution of an ODE, we always have to be careful about where is it a solution. Here it's a solution for any value of t. You notice this because the steps we took are independent, are valid for any value of t that we can think of. So this is a solution for any t. Let's try to go more in general. In general, actually, this approach does not work as straightforwardly. So we have to adapt it a little bit. The idea is that we add a factor that we'll call the mu of t that will make our integration easier. So as before, we want the left-hand side to be the derivative with respect to t of the function that we know. Usually that doesn't work directly, but if we multiply the left-hand side by a function mu that we can choose, we can tune it in such a way that it works out again. So let's start with a more general approach, but with a bit more restricted than the most general first order ODE. We will look at y prime plus ay equals gt. And with the idea of the integrating factor, we multiply everything by mu t. Mu t is a function that we don't know yet. It's a function that we can choose, and we'll try to choose it in such a way that it works the best for us. So in particular, we want to choose it in such a way that the left-hand side is the derivative with respect to t of the function mu that we can choose times yt, that is the solution that we're looking for. We want this rewriting. So we need that mu prime is equal to a times mu. But this is a simple thing. that means that mu t is equal to any constant times the exponential of at. If we use this function, then we can plug it in our ODE and try to solve this. Looking at this, we notice that there is this constant c everywhere that we don't really need, so we're going to cross that out. Once we cross that out, we write the left-hand side in the format we want. Derivative with respect to t of a function we know that we have chosen times y, that is the solution we're looking for. And on the right-hand side, we have the function that we just found, exponential of at, times g, that is the function we already had. So, as before, we can integrate both sides. The left-hand side just drops the derivative with respect to t, while the right-hand side gains an integral with respect to t. Plus c. c, as before, comes from the integration of the left-hand side, in which we don't know the value of y at 0. And now, well, we have everything. We just change things around a little bit, and we have yt being the exponential of minus at times this big block, that is the constant c that we don't know, plus an integral going from 0 to t of exponential of as times gs ds. This is a solution of y prime plus a being a constant times y equals g function of t for any t positive. Ideally, where does the constant come from? Well, the idea is that we know how the function changes over time, but we don't know the initial value. So c will depend on the initial value that we start with. Let's look at the first order linear ODEs in even more generality. So we are now replacing a of the previous example with pt, so any function of t. And we want to try to solve this. As before, we're going to look for an integrating factor mu t that will make our job easier. So we can choose this mu t to be any value, and what we want is that the left-hand side can be written as derivative with respect to time of mu t times yt. Yt is the function we don't know and we want to look for. Mu t is a function we want that fits these parameters. In order for this to be a good rewriting of our ODE, then we need, and you can do the calculations to check that out, we need that mu prime is equal to p function of t times mu. This is something we can solve again, and we're going to do that. So first we're going to move mu t on the other side, such that only the left-hand side depends on mu t. So we have mu prime divided by mu t equals pt. Everything depends on time, so we can integrate on time both sides. The left-hand side, assuming that mu is never 0, the left-hand side becomes a logarithm of the absolute value of mu, while the right-hand side is the integral of pt with respect to t, plus k. K is again the idea that we're integrating without bounds, so we can be shifted by a constant, but what we want is mu to be the easiest function that fits our constraints. So we're just going to drop k out of the window. We're going to set mu t being the exponential of the integral of pt with respect to t. Note that this does satisfy the fact that mu is never 0, so we're good in that aspect. With this mu, then going back, we have that the derivative with respect to t of mu times y is equal to mu times g. So integrating both sides, we have that mu times y is equal to the integral of mu times g with respect to t plus a constant that is given by the integration. So we can write yt being 1 over mu t is being the thing we just computed before, times this big parenthesis with the integral from 0 to t of mu s gs ds plus c. this is all the videos for this week. Hope you're enjoying it. If you have any questions, remember to post in the discussion.